the next lecture of switching theory and logic design. So today our concept is asynchronous decade counter. That is, decade counter we can also call mod 10 counter. So decade counter and mod 10 counter both are same operations. Okay. So decade means mod 10. Right. So here our concept is asynchronous decade counter. We know the designing of counters. We have seen in the previous class how to design a 4-bit asynchronous counter, that is up counter, down counter. Two counters operations we have seen. In this class we are going to discuss about asynchronous, how we have learned in the asynchronous counter operation. The same counting behavior we have to follow here. That means we have to connect the different clock pulses to all the flip-flops. That is the very important information here. So there is no single clock for all the flip-flops. Okay, there is no common clock signal for all the flip-flops. Here we are using different clock pulses for the different flip-flops. So that is the asynchronous and decade counter. It should start its count from 0 to 9. It has to perform only 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After again it has to start 0. Right? So 0 to 9, 0 to 9, 0 to 9. Like that it should count. So coming to here, the definition of a decade counter. A decade counter is a binary counter that is designed to count up to 1010. That is, it should count up to decimal 10 values. That is 1 to 10. So whenever it reaches the value of 1010, the value is going to be again 0. So let us see. Say here 0, 0, 0, 0. So this is the decimal equivalent value. This is the decimal equivalent of 0. Next 0, 0, 0, 1. So this is the decimal equivalent 1. Like that, it should perform totally 10 counts. So 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. So this is equivalent 3, 4, 5, 6, 7, 8, 9, and this is 10. So here we have to design a counter which it performs the counting from 0 to 9. So 0 to 9 we have to use or we have to make the counting. So whenever it reaches the 1010 count, when it reaches the decimal 10 count, it should goes to again 0. So after 1001 count, so whenever this 1010 count recognizes, then again it should start the counting 0, right? So 0 to you have to count up to 9. After 9 you have to count 0. Again you have to continue up to 9. Again you have to go to 0. So you have to start the counting from 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9 you have to show again the counting should start from 0. So like that you have to go again counting. So whenever you reach the count 9, then you have to go for the next count is 0. That is, whenever the 1010 reaches, then the counter goes to 0 situation. The counter goes to 0 outputs. That is, all the flip-flops goes to 0, 0, 0, 0. That is the reset operation we have to perform. Otherwise, we have to clear the all flip-flop outputs. Then the zeros will start the counting. So this is the behavior. So decade counter counts from 0 to 9. After 9 we have to again start from 0. So that is a major conversion. This is a major conversion. So here see, whenever 1010 receives, then we have to make the flip-flops output or counter output as 0. That is, we have 4 flip-flops, right? 1, 2, 3, 4. Okay. So in the previous slide we have seen 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So almost all the counts these 4 flip-flops are performing. So here my task is whenever the first flip-flop output is 0, second flip-flop output is 1, third flip-flop output is 0, fourth flip-flop output is equal to 1. Whenever these values are reached, then we have to stop the count and we have to start the values of zeros. We have to start the values of zeros. So this is the work we have to perform here. This is the work we have to perform here. So based on that, the same 4-bit asynchronous counter what we have learned in the previous class, that is we are taking here, right? So see here. So this is a 4-bit asynchronous up counter. This is the 4-bit asynchronous up counter. So this asynchronous up counter, see here, we have connected a first flip-flop complemented output to the next clock signal. And in the same way, second flip-flop complemented output connected to the third flip-flop clock signal. And fourth flip-flop complemented output we have connected to the fourth flip-flop clock signal. So in this way, we have given the connections. So in this circuit, you have to make the counts 0 to 9 and you have to put the value after 9, you have to get 0. So that is the activity you have to do here. So here you have to use a common clear signal. You have to use a common clear signal. So see here. So this is the clear signal. So we know that this is the clock signal. This is clock signal and this is clear signal. So this is an active low signal. This is active low signal. So clear bar indicates this is an active low signal. It is works for 0. So this is also clear bar. 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 So clear bar. So whenever the clear signal goes to 0, whenever this clear signal goes to 0, automatically all the flip-flop outputs are goes to 0. Whenever the clear is equal to 0, all the flip-flop outputs are goes to 0. So I will start the countings from 0, 0, 0, 0 to 1, 0, 0, 1. So this is the 0 to 9 count. Whenever this flip-flop reaches the next count, that is 1, 0, 1, 0 count, whenever it reaches the next count, then automatically the flip-flop goes to 0. The flip-flop, all the flip-flops output goes to 0. That is, after 1, 0, 1, 0, you will get all the outputs as zeros. For that, see here, this 1, 0, 1, 0. So see here, 1, 0, 1, 0. Here we are writing this is a Q3 and this is a Q2, this is Q1 and this is Q0. Here, so see here, I have written the Q3, Q2, Q1, Q0 positions. So the Q3 value goes to 1, Q2 value goes to 0 and Q1 value goes to 1 and Q0 value goes to 0. So whenever this combination occurs, then only the clear signal should go to activate. So see here, whenever the count you don't require that combination, for that combination you have to draw some logic diagram. So see here, Q3 is equal to 1. So this is the third, this is the second, this is the 1, this is the 0. These are the 4 flip-flops. Whenever the third flip-flop output goes to 1, so here I mentioned Q3 output goes to 1. So this is the Q3. Q3 output is 1 and Q2 output is equal to 0 and Q1 is equal to 1 and Q0 is equal to 0. Here we have two flip-flop outputs are 1, that is Q1 and Q3. So whenever these two flip-flop output goes to 1, whenever these two flip-flop outputs goes to 1, so then I have used a NAND gate. So see here, whenever these two flip-flop inputs are 1, this is 1, this is 1. What is the NAND gate operation? NAND gate operation is exactly reverse to the AND gate operation. What is AND gate operation? If both inputs are 1, the output is equal to 1 for the AND gate. For NAND gate, that is a reverse operation. If both inputs are equal to 1, then the output is equal to 0. So then this NAND gate output goes to 0. So this 0 is applied to here, this 0 is applied to here, this 0 is applied to here. So the NAND gate output is connected in this way. So this is the NAND gate output. So this 0 is applied to the clear signal. So this is the clear bar signal. So clear bar signal will work for the 0. Clear bar signal will work for the 0. So whenever this value is equal to 0, all the flip-flop outputs goes to 0. All the flip-flop outputs goes to 0. So the present outputs of all the flip-flops are 0. In this way, the counting operations are going to perform here. Okay, so this is the explanation for the decade counter. So once again, see the decade counter operation. So here, at which count you want to stop this counter, and after that, which count you want to start. So here you have to start the count from 0, 0, 0, 0, and whenever it is reaching 1, 0, 1, 0, you have to stop this count. You have to stop this count. In the place, you have to again start all zeros values. How you will get all zeros for the all flip-flops in a counter? You have to use a clear signal. With this clear signal, we can make all the flip-flop outputs are zeros. So if all the flip-flop outputs are zeros, then you are giving the clock signal all zeros. After you will get 00001. Like that, after you will get 0010. Like that, the coding sequence will start. Why? Because our connections are seems to be like as a 4-bit asynchronous counter. So for that reason, so whenever this 1010 count reaches, you have to make the clear signal is active. For making the clear signal active, I did that. So 1010 means Q3 1, Q2 0, Q1 is 1, and Q0 is equal to 0. Whenever these outputs are occurred, then you have to give the clear signal. For clear signal, you have to give the 0. So but Q1 and Q3 outputs are 1, 1. So take this to 1, 1. Why? Because whenever you are writing the Boolean expression in a truth table for the output, we are taking the output is equal to whenever the switched on conditions. For switch off conditions, we are not taking. So Q2, Q0 values are 0. We are not considering. Here you have to take Q1 and Q3. These two outputs you have to connect to a NAND gate. If both inputs are 1, the AND gate output is equal to 0. So whenever the 0 will enters into the circuit, the clear signal makes all the flip-flops are going to 0. So this is the behavior. This is the basic behavior of the mod 10 counter in asynchronous mode. Asynchronous mod 10 counter. Okay. Right. So see here the basic truth table how it formed. So here we have the clock signal. Here we have the clear bar signal. And here Q3, Q2, Q1, Q0. Right? So go to with clear signal. If clear signal is equal to 0, so irrespective of the clock signal, all the flip-flop outputs are goes to 0. So if clear is equal to 1, and if the clock is observed, generally this is a positive edge triggered clock signal representation, up arrow, then the counting is going to start here. So whenever the clock signal is observed, the counting is going in this direction. Okay. Right, like that. So here I am mentioning all the counts here 1001. Right. So whenever it reaches 1010, okay. So whenever the 1010 it receives, then automatically the next count is going to 0, 0, 0, 0. So for that, so this whenever this value is occurred, then I make the clear signal is going to active, that is equal to 0. So whenever this 1010 count is occurred, I am making the clear signal value is equal to 0. So this clear signal is basically active low signal. Whenever the clear bar is equal to 0, automatically all the flip-flop outputs are goes to 0. Then after again, if you give the clock signals, then the counting sequence going to continue. Okay. So this is the behavior of mod 10 counter. This is the behavior of mod 10 counter.